All right. So last time we obviously got into gases some more here, and we talked about some formulas. We talked about really a really good one, which is the combined gas law. And as we talked about last time, you could really use the combined gas law, especially this version of it that has the N in it, which is really based off of the ideal gas law, basically PV equals nRT, and setting them both equal to each other through R. You really can get all those other gas laws that we talked about really from this equation. You essentially just need to kind of cross out whatever is constant, whatever is not mentioned, and you'll pretty much have all those other gas laws. So again, if you cross out the bottom here, you have Boyle's law. If you crossed out the P's and the N's, you would have Charles' law and so forth. So really good two equations really to sort of memorize, as it can be very, very helpful in solving for what you are looking for. So if you know these two, you essentially could get to every gas law that you might want to know. So again, I would invest my time maybe in just remembering those two, and you pretty much should be able to find it. Um, we also got into gas density and molar mass. And remember, there are two sort of dedicated formulas, both for density and molar mass. Remember, though, when we do density, usually it's grams per liter, the units that we shoot with for gas, and molar mass is our normal grams per mole, are the typical units that we shoot for molar mass. So you could use those two formulas that we talked about last time, or as I kind of showed you as well, you can still roll with, the ideal gas law. And you basically use the ideal gas law and some stoichiometry or really dimensional analysis to get to what you need. Again, if you're looking for a gas density, you could actually solve the ideal gas law for N over V, which would be P over RT. That is moles per liter. And then basically all you have to do is times it by the molar mass, and you will get yourself there to your density, basically. In terms of the molar mass, if you're calculating it, I would say in most cases that grams part is just going to be given to you in the problem. And then really just use the ideal gas law there and solve for N, PV over RT, and that would get you the bottom part. So again, just knowing the ideal gas law and a little bit about some dimensional analysis in units can allow you to get to those guys without having to, again, maybe remember a couple other formulas you maybe don't want to remember. You can kind of just stick with those two, and you should be able to get to those guys as well. We lastly talked about stoichiometry and gas stoichiometry. And really, gas stoichiometry is the same as regular stoichiometry. I would say probably your major difference is going to be at either step number 2 or step number 4. Obviously, we have our balance our equation. We're going to convert to moles. We're going to do our mole to mole relationship, and obviously moles to some other unit. So I would say probably either in step number 2 or step number 4, or sometimes you might even use it in both places. You're going to probably use the ideal gas law. So if you're going to use it in step number 2, you probably will be solving for moles. If you're going to use it at the end, very commonly, you're going to be solving probably for something like volume or something like that, which is a very common sort of ending to a gas stoichiometry problem. All the rest is the same and like normal. Obviously, again, if you're doing some type of stoichiometry problem, you also always want to make sure that it is not necessarily a limiting reagent problem that you have to worry about that as well. So um, kind of works the same. Any questions on that stuff there? All right, so I think we finished up with gas stoichiometry last time. So we're going to continue on and talk about the next sort of idea here with gases. And that is Dalton's law of partial pressures, which sounds super difficult, but it really is not so difficult. When we talk about partial pressures, we're really talking about a situation where in a lot of cases, gases do come as sort of a mixture of gases. And if we just had, for example, in a container, only gas A flying around, basically, the total pressure of that container is all basically a result of gas A, or the pressure associated with gas A, as that's the only guy basically flying around in that container. Now, if we did have sort of a mixture of gases in there, maybe A, maybe B, maybe C. I know my alphabet, that's good. And in this case, each of those gases, bless you, that are flying around are going to contribute to the total pressure of that mixture of gases. So in this case, our total pressure would be the pressure of gas A plus the pressure of gas B plus the pressure of gas C. These pressures here are what are referred to as partial pressures. They're called partial pressures because they partially contribute to the overall pressure of that system. And what is the most common way that we could calculate a partial pressure? Well, frankly, it is again that famous gas law there, the ideal gas law, PV equals nRT. And we could use the ideal gas law here to do that. We essentially would just use the ideal gas law for each of these gases individually. We would solve for the pressure of A, which would be nRT over V. We could solve for the partial pressure of B, also nRT over V. And lastly, the partial pressure of C, which would be nRT over V. Now, what is the good part about all these gases being in the same container? Because they are all in the same container, they will all have the same volume because they're flying around in the same container. And because that container is probably sitting in the same room, they will all have the same temperature. So if you just think about the ideal gas law here, all these gases in this mixture have the same temperature. They all have the same volume. R is a constant. We would be solving for P. So really, in most cases, the only thing that's going to kind of differ between the gases is how many moles there are. So that's the only kind of difference that you'll have in there. And basically, you could just do an individual ideal gas law for each gas in there. Now, because these are assumed to be under ideal conditions, one of the things that makes something an ideal gas, as we might have touched upon, is the idea that in an ideal situation, there really is no attraction between different gas molecules. There's no repulsion between different gas molecules. They essentially just don't interact with each other under ideal conditions. And what that means is, even though in the case over here on the right, we got three different gases flying around, we could essentially assume ideal conditions and essentially just think of them as just being in there by themselves without any other gases. They're not going to basically affect anything. And that's what allows us basically to do calculation like this, which is, again, that ideal situation. Now, as I mentioned, we're just going to kind of roll with our ideal gas law in each situation and calculate our total pressure by adding them together. Now, what happens if you actually come across a situation where maybe you don't have enough information to go into the ideal gas law, but maybe you know something about one of the pressures of the gases that are present, or maybe you know the total pressure. By the way, the total pressure would be like the barometer reading. If you were like in the laboratory, that would be your total pressure. Now, if you know the moles of the gases that are present in that mixture, and you know, like I said, either the total pressure or one partial pressure, you could actually still figure out the partial pressures of everybody and maybe the total pressure by using something we saw in the previous chapter, which is our mole fraction. So this is our mole fraction. Remember, a mole fraction is the moles of what you're interested in divided by the total moles. Yeah. It is like a percentage without the multiplying by 100, so it's really not a percentage, obviously. The moles you're interested in. So you could use this other sort of partial pressure formula. The partial pressure of a gas is equal to the mole fraction of that gas times the total pressure. So what this allows you to do is, like I said, if you know the moles of the gases are present, Or if you know something like grams of everybody present, that's just as good as knowing the moles because you can convert to moles. And like I said, all you need is basically one piece of pressure information, either a partial pressure or a total pressure. You can then figure out everything else. So if you come across a sort of partial pressure problem, and you don't feel like you have enough information to go into the ideal gas law, then you might want to look at sort of a formula like this where you can, like I said, as long as you got moles and a pressure, go into it. Otherwise, you can go obviously into our ideal gas law for each gas individually. Any questions on that there? Uh, Why don't we try one here? We take 5 grams of helium and you add it to 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. What is the partial pressures of each gas and the total pressure? So again here, helium is 4.003 and neon I think is still 2018, I hope. All right, so take a few moments here. We're looking for really 3 answers here: the partial pressure of neon, partial pressure of helium, and the total pressure in this situation. Okay, let's take a look. We got 5 grams of helium and 5 grams of neon. So obviously here we got a mixture of gases flying around in that same container. We know that the volume here is 2.5 liters and we have 27 degrees Celsius as our temperature. And we're looking for the partial pressure. So really, again, we're going to kind of use our PV equals nRT for each gas. Once again, the temperature and volume is going to be the same. R we always have, but never given to you in a problem, usually. And obviously here we're going to be looking for P. So we do need to get to our N. So first thing we want to do is really just convert each of those grams into moles. So our moles of helium should be 5 grams of helium using the molar mass from the periodic table, 4.003 grams per mole of helium. That's going to be 5 divided by 4.003. 1.249 moles of helium. We'll do the same thing here for our neon. So we got this 5 grams as well. Going to divide this though by neon, which is 2018 grams per mole. That's going to give us here 0.247, and we'll call it 8 moles of neon. So now we have basically the moles of each of those gases, which is the last thing that we need. So we're just going to go in here and basically use the ideal gas law twice. Again, we could do this because we're under ideal situations. So even though there's different gases flying around, they're not going to ideally interact with each other. So we'll go with our pressure here of helium, nRT divided by V. We're going to go with our moles, which is 1.249 moles of helium, our 0.08206 liters atmosphere Kelvin mole. And our temperature here, which of course we do need to convert to Kelvin, should give us 300 there. 300 Kelvin. All that's going to be divided by our volume, which was 2.5 liters. 2.5 liters. Moles are going to cancel. Kelvin going to cancel. Liters going to cancel. Going to leave us atmospheres left over. And that's going to get us here something. 300, a little 250 divide. It's going to give us a 12.3 atmospheres. This number would represent the partial pressure of helium in this case. Any questions on that calculation there? Pretty much just going to repeat that same calculation for our other gas. Really, the only difference here is going to be the moles. So we'll go the partial pressure of neon, also nRT over V. So we'll be sure to use our neon's moles, 0.2478, our 0.08206 gas constant, our 300 Kelvin, divided by 2.5 liters. Once again, everything's going to cancel out except the atmospheres. And that's going to get us here. Looks like 2.44 atmospheres here. And this would be the partial pressure of neon in that case. Any questions on those two? Now to get my total pressure, all I have to do is simply just add those two numbers together. So our total pressure will be the partial pressure of helium plus the partial pressure of neon. So adding those together are going to get us 12.3 atmospheres plus 2.44 atmospheres. And that's going to yield us here 12.3 plus 2.44. And we'll call it 14.7 atmospheres of total pressure in this particular case. Yeah. Any questions on that there? Obviously, we can see from this problem, although we have the same number of grams of each of these gases, the major contributor to the pressure in this case is helium. Yeah, helium is the major contributor. The reason why helium is a major contributor is, as we'll talk about shortly, has to do with these numbers right here. Helium is much lighter, which means because it's much lighter, it's going to be flying around a lot faster. And because it's flying around a lot faster, it's going to cause more collisions than the heavier and slower moving neon. So you can see it causes a lot more collisions than and a lot more partial pressure in this mixture than that from the slower moving neon. Any questions on that there? All right, so let's take a look at this one here. A sample natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of, that would be propane, I believe. If the total pressure of the gas is 1.37, what is the partial pressure of propane? So give it a go, see what you come up with here. Moles of, that looks like a highlighter, maybe not use that. All right, so let's go with something that writes. So we got moles of methane here, which is 8.24. We got ourselves some moles of ethane, which is 0.421 moles, and some moles of propane here, 0.116 moles in this case. And we have the total pressure given to us, which is 1.37 atmospheres in this case. So again, if we're kind of thinking about the ideal gas law here, P equals nRT, well, we don't really. So this is not going to be very helpful for us. But what we do have is the other information that can be helpful. We do have moles and we do have some type of pressure, which will allow us to use that mole fraction formula, which looks something like this. So in this case, we are interested in the partial pressure of propane, C3H8. So we'll need the mole fraction of propane and times it by the total pressure. So first thing we could get here is our total moles by just adding them together. So if we add them together here, 8.24 plus 0.421 plus 0.116, this can give us an 8.777 moles. And again, here we're going to be looking for our mole fraction for propane. So that means we're going to take basically the moles of propane, 0.116. We're going to divide it by the total moles. And it's really a percentage, but obviously we're not going to multiply by 100 in this case. 0.116 divided by 8.777. Going to get us 0.0132 as our mole fraction. Basically 1% of it is made up of propane. And we're going to then put it in with our equation. So we'll go partial pressure C3H8 will equal our mole fraction times the total pressure, 1.37. And if we do that there, 1.37, looks like maybe we end up with 0.0181 atmospheres here as our partial pressure of propane. We obviously could have done this for the other gases. We can see we obviously have a lot more moles of methane. So if we happen to do it for, say, methane here, oops, we'll do our mole fraction for methane, which would be in this case 8.24 divided by 8.777. That would give us a mole fraction for methane of, and obviously it wasn't asked for, but it's basically 94% methane. So our partial pressure here of methane would be 0.9388 times our 1.37 pressure there. Try to squeeze it in there. And we'll take 1.37 times that number, gives us a partial pressure of 1.29 atmospheres. And we can see obviously here way more moles of methane moving around in that container contributed a lot more pressure of the total pressure than our actually smallest number of moles that are flying around there as well. By the way, same idea here. Methane is much lighter of a gas than propane. So again, in addition to having more moles of methane flying around, they're also probably moving a lot faster than the moles of propane. And again, causing more collisions and resulting in more pressure in this case. Yeah. Any questions on that? And obviously, if we did our ethane, it would probably be somewhere in between. By the way, we could simply find our ethane partial pressure because now that we have two of them, the total pressure in this case should be our partial pressure of methane plus the partial pressure of ethane plus the partial pressure of propane. And since we already know two of the three, we don't even really have to do much of a calculation at this point. We could just take what we already calculated, add them together, and subtract, right? So we add that with our 0.181. Oops, I missed a zero there, didn't I? 0.0. 0.0181 atmospheres plus the partial pressure of our ethane. So we take our 1.29 plus 0.0181. That gives us 1.31 basically. So 1.37 minus our 1.31 will tell us that we have something like 0.0619 atmospheres is the partial pressure of ethane. So we actually don't need to do our mole fraction on that one. We can just add there 2 and subtract from the total will give us our total pressure. Any questions on that? So this is a helpful one or a useful one if you maybe don't have enough information to go into the ideal gas law. Again, missing maybe some temperatures or volumes and things of that nature, but you could at least get the moles of everybody involved. And really the other thing that you need is just one type of pressure information. We have the total pressure in this case. We could also use just a partial pressure as well. So if we had a partial pressure or total pressure, we can basically figure out everybody else's. Any questions on that there? All right. So that's another type of partial pressure type of problem. The third type of partial pressure problem occurs a lot of times in the laboratory based on how you collect your gas. And for example, this is a popular experiment, very famous. We take a little potassium chlorate, which is a solid. You heat the heck out of it in a test tube. It will go through a decomposition reaction, make a little potassium chloride, and it will generate some oxygen gas. So as you start to torch this thing, it will decompose and it will basically make some oxygen gas, which this test tube is hooked up with tubing where the oxygen gas will go through the tubing, which is underwater at this point usually, and it will go into sort of a collection jar. And that collection jar was originally filled with water, like you see here, filled to the brim with water. And as the gas comes in, the water will go out and be displaced, and you will end up with this empty spot in your container. And it's really not empty. That is actually where the gas is at this point. Gas will bubble up here. And in here, in this particular example, that is where you would find the oxygen gas or whatever other gas you might be collecting. But as a side product of how you collected this gas, because there is, our friend, water involved and some type of chemical reaction, which has a tendency to heat up water. And when you heat up water, you get a side product that you're really not interested in, and that is water vapor. So you very often will collect some water vapor with your gas that you're actually looking to collect. You're not interested in the water because it's really just a result of how you collected it. The actual gas you're interested in is really a side sort of product. So instead of the total pressure, which is the barometer reading equaling the pressure of the gas you're interested in, is also a partial pressure situation where it will equal the gas you're interested in plus the vapor pressure of water. The water vapor pressure, the vapor pressure of water is typically a value you can look up on a table. And usually based on temperature you're doing the experiment, you can look up that value, kind of like what you did the other day when you looked in the back of the book there for some density and water and stuff like that. You can look it up in a table. And this is usually a correction value. So in this, if we were doing this experiment, we're really only interested in the oxygen and the pressure associated with the oxygen. So we would rearrange that equation and find the pressure of oxygen would be the total pressure, which once again is your barometer reading, minus the vapor pressure of water at that temperature. And this is sort of like a correction factor that you kind of do when you collect water in this fashion. You'll do something in the next experiment like this. You'll collect it over water, but you actually will not do this calculation. You'll get the old school way. You get like a ruler and do a little correction that way by measuring the difference in the water levels in terms of what you collected. How do you know it is this type of situation? Usually in the problem, they will mention something about water vapor. They'll say, hey, you collected the gas over water. You collected a gas that's saturated with water vapor. That's usually the key terminology to tell you you have this situation occurring, and you usually have to do some type of subtraction of the water vapor pressure to get the pressure of just the gas you're interested in. Now, clearly in this example is oxygen, but it could be any gas that you were collecting. And here is an example of a vapor pressure of water table. And again, you have one in your book. And it's usually, again, like I said, based off of temperature. So let's take a look at an example here. We have a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. If the total pressure is 753 torr, the vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the oxygen gas in atmosphere? So take a few moments there and calculate it. Okay, so let's take a look. So on this one, this is really the key wording there, saturated with water vapor. Again, that tells you we have a situation where we were just talking about. We really have a mixture of gases. So again, our total pressure would be equal to the pressure of the gas plus the vapor pressure of water. And in this particular case, they were nice enough to give you the vapor pressure of water. If they did not, you would need to go to that table or a table like what we just saw there to look it up. We also have the total pressure, so this is not too bad. This is looking like a subtraction situation here. So we will take our numbers. We got 753 torr, which is our total pressure, our partial pressure of oxygen, plus 31.824. Not atmosphere, torr. We're basically just going to subtract. So the partial pressure of oxygen in this case is going to be 753 minus 31.824. It's going to get us, we'll call it 721 torr in this case. That would represent the partial pressure of oxygen. Sometimes people, especially like in experiments and stuff like that, they'll refer to this as the pressure of the dry gas sometimes is referred to, and that's again because you subtracted off water's component to it, and so sometimes people refer to it as just the pressure of the dry gas by itself. We do want it in atmospheres, so a reminder that 1 atmosphere is equal to 760 torr, also 760 millimeters of mercury. So we're going to divide it by 760 here, and that's going to give us atmospheres. And that'll get us 721 divided by 760. We can go with a 0.949 atmospheres in this case, would be the pressure of just our dry oxygen gas by itself after we get rid of the pressure associated with the excess water that was just collected as a result of how we actually collected the gas in this case. Any questions on that one there? So that is 3 different sort of partial pressure situations. One where you could kind of just go into the ideal gas law. One where maybe you don't have enough information to kind of go into the ideal gas law, but do have grams or moles and some type of pressure. And one here where it's really more of a very common situation you see in the laboratory, just as a process of how you collect the water. You got to do sort of a correction to the pressure value. Any questions on any of those there? Yeah. It doesn't. They could be in any unit, like anything else, as long as they're the same. But clearly, if you're going to go into the ideal gas law, since everything has to be kind of atmospheres, it will end up being atmospheres in that case. So commonly you'll see in atmospheres, but it could definitely be in different units and stuff. So if you had something like, you need 2 partial pressures, maybe the total pressure, and maybe one was in atmospheres and one was in like millimeters mercury, you just got to choose whichever one you want to convert it to, and then depending on what the question may want the answer in, then you would go based on that. But definitely, like normal rules, if we go into the ideal gas law, it's going to end up being atmospheres at the end of it. Other questions? All right, we're going to